Welcome, this is lecture number 17. In this lecture, we are going to talk about combined feedback and feed forward control. So, we have so far discussed feed forward control without feedback first. I think it was in lecture number 14. Then we have discussed in lecture number 15 with single loop and two loop control. Okay. So, that means we are familiar with voltage mode control, which is a single loop control, and we are also familiar with input voltage feed forward. So, in this lecture we will consider combined load input voltage feed forward in voltage mode control. Here also the load current feed forward in current mode control. Okay, and in subsequent lecture we will see such combined feed forward control can actually significantly change the loop gain characteristics, because we will see in voltage mode control in future we will see the loop gain is dependent on input voltage, but by incorporating feed forward input voltage we can make the loop gain more or less insensitive to input voltage. Similarly, in current mode control we will see, that is why in general voltage mode control suffer from poor line regulation and current mode control suffer from poor load regulation, but by means of load current feed forward we can make this loop gain more or less insensitive to load current, and we can achieve excellent transient performance as well as disturbance rejection. Then also we want to see adaptive voltage positioning or droop control, because this droop control is used in general it is used very much in microgrid application, even in LED driving application, but it is also used in processor power supply where the terminology is called adaptive voltage positioning. Okay, because this can be used to almost achieve purely resistive output impedance. So, that means it can respond to the transient almost immediately, and we will see this in today's lecture using MATLAB simulation. So, all this input voltage, load current feed forward as well as adaptive voltage positioning or droop control, we also want to show MATLAB simulation case study demonstration. So, first input voltage feed forward, we know already about this loop gain, though we are not familiar with this transfer function because we have not covered yet the small signal model, but assume that, because that will be discussed in the subsequent lecture, but assume that there is a transfer function which can be derived, which actually capture the frequency behavior of the frequency response behavior of the output voltage with change in duty ratio. This is a modulator gain, and that we have discussed, because that if we are using a sawtooth waveform, and the sawtooth waveform the voltage magnitude, the peak voltage, the modulator gain is 1 by that peak voltage. Then the controller part, although we have not discussed about the design of controller, but here we are taking some controller and I will show you that controller can be designed by, if you provide some crossover frequency, phase margin, but the exact design process will be discussed in the subsequent lecture. But today we will take a compensator and we want to see the feedback closed loop control, voltage mode control and its transient performance, particularly the supply transient performance. Then we want to see without feed forward and with feed forward what is happening. Now, here the voltage mode control we consider a sawtooth waveform where MC is the slope of this ramp, and this slope of this ramp is nothing but, what is the slope of this ramp? The slope of this ramp is nothing but the upper limit of voltage minus lower limit by T. So, here the lower limit we took VL equal to 0, but sometimes you can add some offset to keep it up or keep it down. Okay. Sometimes this voltage can be symmetric with respect to 0, right, not symmetric. I will say we can take this base value, that means VU, half of the VU will be negative, half positive. So, there are many possibilities, but in most of the commercial application we generally take 0 to some maximum value voltage. So, in that case it is simply MC will be nothing but V upper by T if V lower equal to 0. And what is modulator gain? The modulator gain here is, the modulator gain is 1 by, if this is the case, it is 1 by MCT, which is nothing but 1 by simply VU. Okay, that is the maximum voltage. Now, we have discussed in lecture number 14, in the feed forward we need to incorporate the upper voltage, which or basically the slope of this ramp is proportional to the input voltage. And we also discussed in integrated circuit how can I do that, because generally these waveforms are generated by using a constant current charging a capacitor. So, the output of the capacitor will look like a sawtooth waveform. Now, the slope of this sawtooth waveform decided by two factors. That means, if I charge a constant current charging a capacitor, okay. So, this magnitude of this constant current and the capacitor, that means what is the slope? The slope is nothing but the IC by C, okay, because you know this voltage which is our ramp voltage VR, dVR dt, which is the slope, is simply IC by C. Here IC is the current source and it is constant, and capacitor C is constant. So, if the capacitor is constant, then the slope can be varied by varying the magnitude of the constant current. That means, we can vary this quantity, we can vary it. And if we vary in proportion to input voltage, then we can realize this actually this feed forward action, okay. So, here it is in the Simulink model I am showing, but in actual circuit I told you that it can be implemented, okay. So, by this in Simulink we are going to implement this, but in circuit level we can implement by using this current source. In fact, we can do it in Simulink also, no problem. So, ramp. Now, next, input voltage feed forward. In the previous lecture, when we consider open loop, we have disconnected this loop. We have taken a constant, you know, this to be constant, something like a constant, okay. So, we have disconnected this loop and then we applied a constant voltage, and then we have considered the input voltage feed forward into this sawtooth waveform. And we saw there is a drastic disturbance rejection even using open loop converter by means of input voltage feed forward when the converter undergoes a step change in the supply voltage. This is also true if your supply has, suppose in a distortion, that means your supply has some distortion along with the fixed value. And in previous lecture, in lecture number 13, we have discussed if you consider an practical voltage source, and the practical voltage source has some impedance, or if you poorly connect the wire cable of your power converter, and if the supply is not very well regulated, then this output impedance of the supply, which may include the cable resistance also, can drastically change the behavior of the source voltage of across the buck converter when it is driving a DC-DC converter, because your buck converter has a pulsating input current or discontinuous input current. So, that will introduce a oscillatory behavior. In fact, the profile of switching will also appear there, and such behavior in the source can get reflected in the output if that means it can be reflected in the output, which is here. This is output. So, sorry, this is not Q. Q is actually going to this PWM box. This is Q, the output voltage. This can substantially, you know, this effect can be reflected in the supply and output, and that is not desirable. By means of feed forward, you can almost reject the disturbance. That is first thing. Okay, that is one thing that we will discuss. In closed loop, we are considering compensator and then adding this feed forward, and we want to see what happens. Okay. So, we want to simulate a case study with and without transient. Okay. Let us go back. So, you do not need to know detail about this model, because we will discuss with all detail in the PowerPoint when we come to the design stage. For the time being, we are assuming there is a compensator in the feedback loop, and I have designed the compensator which will require the bandwidth or basically crossover frequency. I have set 50 kilohertz because 500 kilohertz is my switching frequency, and I am keeping some 60 dB phase margin. Now, the compensator is designed, and this go to the buck converter directly, and this takes the compensator directly from the MATLAB file. That means, you know, if you remember that why we wanted to do the MATLAB based simulation interactive, because we can plug in everything from MATLAB and run the simulation from the MATLAB.m file itself. We can make the design more interactive. Okay. So, 60, and we will come to this roughly in 34, 35, 36 lecture number. We will discuss detail about this process of design as well as the MATLAB coding. But today I just want to discuss about what will be that impact. So, we are making a transient, supply transient. Okay. So, we are making a supply transient where I have applied a supply of minus 6 volt. That means the converter input voltage will change from 12 volt to 6 volt. So, minus 6 volt transient means initially 12 volt, then it changes to 6 volt. Okay. Now, first thing I will see, without feed forward I want to run it. Okay. I will run it without feed forward. So, if I run the converter and I will show you the supply transient response using closed loop control. Okay. So, because of the closed loop, you can see the output voltage is tightly regulated around 1 volt, the average sense. Okay. Which in open loop we saw that if we apply a fixed duty ratio, it will never happen, but in closed loop it is actually getting controlled. Also, now this transient behavior is under the closed loop control, and you see because of the supply step there is a huge overshoot undershoot in the output voltage, and because even though we design the converter, but this effect is coming. So, we may have to design it, we have to try to reduce this effect by pushing the bandwidth higher. So, one way to improve this, if we can increase the bandwidth, but that can, okay, let us do one thing. If we try to push the bandwidth much higher, that means if we run another case study with, let us say we are going to 200 kilohertz with 60 dB, although the model will not be valid, that I will show you. Next, I want to run the same thing using, so I have increased the bandwidth of the closed loop converter, and I want to see the response. The effect due to the supply is reduced by increasing bandwidth, and we will see this impact when you design closed loop control, because by increasing bandwidth, loop gain crossover frequency, or basically increasing by lifting up the loop gain, you can reduce the impact of the closed loop audio susceptibility. So, that part I am not discussing here, but this is with much higher bandwidth. Okay. Now, we want to move back to our earlier bandwidth, which is low bandwidth. Now, because this bandwidth model may not be valid, okay, here now we want to run the earlier simulation with low bandwidth 60 dB, which is the green one, but now with load current feed forward, and we want to emulate this in the dotted line. That means, let us say dotted black line. Now, we want to incorporate the feed forward action. This is, we are comparing with sawtooth. Now, if we use a product of this, that means this is the product input voltage, and I have taken the feed forward action 1 by 12. Why? Because at 12 volt input, this product into input voltage into gain will be 1. So, that means it will take the same sawtooth at 12 volt, but at 6 volt it will be half sawtooth. Okay, but we are adding a feed forward action, and let us take it. Okay, consider it, and let us run the simulation. Now, I am running this simulation. Okay, now the third one we are drawing. So, now this is the third one I am drawing, which is the case if we consider, now this is a condition. Okay, just hold on, we will take the output waveform. This is with feed forward action. Okay, so we have added input voltage feed forward under closed loop. So, I am showing 3 different scenario here. The blue one with 50 kilohertz bandwidth for a 500 kilohertz switching frequency, that means 1/10 of the switching frequency. The red one, both feedback, no feed forward. Red one, we have increased the bandwidth to 200 kilohertz for 500 kilohertz switching frequency. Although such bandwidth, the model will not be valid, but I am just for sake of, because now we are not talking about model validity, as if we increasing the gain just for sake of reducing the effect due to audio susceptibility. So, that kind of bandwidth generally is not acceptable, because it is a very high bandwidth and it requires a very high loop gain. It may tend to saturate the actual error amplifier also. But in the third case, we have used the low bandwidth, the same as the blue one, but same bandwidth, but with load feed forward, and you see the effect is almost insignificant. There is almost no effect in the supply behavior. So that means this supply transient in feed forward can drastically change the behavior. The another scenario I want to show you. Okay, so this is the one scenario I want to show you. Suppose instead of a step, if I apply a, let us say, just hold on, a sinusoidal input, that means the sine wave with a frequency of, let us say, 2 pi, we can add 1 kilohertz, 1E3, okay, with the amplitude of, let us say, 2 or 3. Okay, so I am adding this. Okay, so I am just, for the time being, I am now creating a simulation case study. Okay, now here what I am doing, I am closing the whole thing and running the simulation. So I am running with 50 kilohertz bandwidth, 60 dB phase margin, and I am using a blue trace. So initially I will not use any feed forward action. That means if I go back, initially I will not take any feed forward action. Okay, and if I run it, I want to show you there is no, okay, so I need to stop the transient also. Okay, there is no transient. So you see the output voltage even with closed loop has a slow scale oscillation, and if you see the frequency of oscillation, it is from 1 millisecond to 2 millisecond peak to peak. That means clearly that output frequency, that means the injected frequency component is reflected in the output, and which, that means if you recall that we talked about source oscillation. So even in voltage mode control we can reduce the impact, but still some part is still there under voltage mode control. Okay, now how can we reduce this effect? Can we reduce this effect by means of feed forward action? So that we want to see. Now we are doing feed forward action and we want to plot it using a different color. Okay, so let us use red color. Okay, and run the simulation again on top of this. So here with feed forward action, you will see the effect is rejected. That means your supply effect is almost nullified. There is no disturbance in the supply even with input voltage fluctuation. So it is almost rejected because the feed forward. So that means even if we increase the frequency of oscillation or amplitude of oscillation, this feed forward action can reject the supply variation. So we have checked that. DC-DC converter without feed forward, with feed forward under voltage mode control. Now I want to show another effect, which is the same, I want to create in current mode control. Okay, so you want to run this first with the voltage mode control, and let us run this simulation. Now we want to repeat in current mode control. Go to current mode control and we want to run this condition. Okay, so if you go here, the same transient is happening, but in current mode control it has an inherent feed forward action. That means it does not require any separate input voltage feed forward here. Okay, that is the beauty in the current mode control. That means the current mode control offer inherent feed forward action that we can see here. The step 1, we want to show with feed forward and without feed forward. That means this is a normalized gain, the load current feed forward, which can be added with the reference current or it can be subtracted from the inductor current, and this normalized gain, I am talking about this gain is equal to 1 for a buck converter, and this is equal to Vref by Vin for a boost converter. This gain is used to scale the average inductor current, load current to the same normalized ratio of the average inductor current. That means for a boost converter, we know that average inductor current is equal to average load current divided by 1 minus d, and 1 minus 1 by 1 minus d is V ref by V in. That means we know that average inductor current for a boost converter is equal to load current by 1 minus d. That means it is nothing but I0 into 1 by 1 minus d, and 1 by 1 minus d in a boost converter is nothing but output by input. So, V ref by V in. Okay. So, this normalization factor we have to do for a boost converter. Now, I want to show 3 cases here. The first case, let us go back to the current mode control simulation. Now, we are not talking about voltage mode anymore. In current mode, we first want to consider, okay, just 1 minute. Okay. So, initially we want to consider no load current feed forward. Okay. So, let us remove this term, everything is removed. Okay. So, it is like a error voltage here, then there is a PID controller, but again I told the current mode control we don't, in current mode control we don't need a PID controller, just PI controller. So, I kept the derivative gain to 0. So, you don't need to define anything here. Okay. This is because this is a default block of PID controller, and here I am using inductor current straight away here, though there is a summing block, but I am not making any changes here. Okay. So, this is a current mode control implementation, and let us say we are applying a load current of 20 ampere, and initially it is 1 volt, reference voltage is set to 1 volt and input voltage is 12 volt, and let us run it. So, I am showing the load transient response of a current mode control. Okay. So, here at this point we have applied a 20 ampere load step, and this is visible from the inductor current waveform. Here at initially it was 1 ampere was the average current was 1 ampere. Now, we have applied a load step of 20 ampere. So, average current should be 21 ampere, and we are getting that. Okay. So, this is a load transient response using current mode control. Here we have not used any feed forward action. Okay. Next, on top of that, in this plot comment, if you go to the plot comment, I want to show the blue color trace with load current feed forward. Okay. So, now I am showing you the scenario with load current feed forward. Earlier it was without load current feed forward. Okay. So, now you can see the transient performance is significantly improved. Is a very fast transient response with load current feed forward. You know, it can reach like almost within a few cycle, right? Few cycle it reaches steady state. So, you can achieve very fast transient performance. And if you go to the current waveform, inductor current waveform, you can see very closely, if you look, it responds very fast, but average is 21, but it goes around 26.5 above that peak current 26.7, which may be too large, but that is fine. Now, my next question is that, so you can see you cannot avoid this jump, because there is a jump, discrete jump, and that is due to the ESR, that we will see. That means, this jump is ESR multiplied by the load step, or in fact, it is the equivalent between ESR and load resistance, and whenever we will do impedance analysis, we will check that, but this drop is unavoidable, that will happen. Now, my question is that if this drop is unavoidable, can we keep the output voltage here rather than going back to the original 1 volt? Why do we need? Because this will unnecessarily require a large overshoot also. That means, we will consider the third option, which is now we are adding a droop action, where we are trying to adjust the reference voltage by introducing a droop action, which actually create a drop when there is a load step transient. So, that, but now I want to consider this R droop, because this droop should be greater than equal to RC, that we will see in the impedance analysis. So, we will see RC is the ESR, that means this ESR drop is unavoidable. So, you should not keep a droop value smaller than ESR. Okay. Now, let us go to the simulation and check for the third condition, which is here. I put here a droop action and it is connected to the load current. Okay. Now, with this I want to simulate and plot, I want to create a green waveform. Okay, green, and run the simulation again. This is with droop control. Okay. So, here I will show you, that means there is a the reference voltage is getting adjusted. So, I will see one interesting fact. In the third case, in the green, the output voltage is getting settled right at the jump point, because there is a jump in the output voltage, and that means up to jump is up to here. So, I have set the new reference voltage to be here. It is getting regulated here. That means I can get the reference voltage right there, and you can see as if there is no transient effect. It is almost immediately settling. That means your output impedance, we discuss about output impedance of a practical source in lecture number 13, where we consider one inductor and capacitor. So, we cannot avoid the output impedance of a DC-DC converter, but we check two things there. One is the DC equivalent, another is the AC output impedance. Because of AC output impedance, we are getting overshoot, undershoot here, but here we are intentionally increasing, emulating, not putting a physical resistance by means of control by droop action. We are emulating that we are introducing a DC output impedance which is same as the ESR of the resistance capacitor, and if you do that, we can get the output impedance almost independent of frequency, because it does not actually seem to have any transient effect. Okay? And if you go to the current waveform, the current is simply keep going there and staying there, no overshoot is there. And another thing is that there is no current overshoot. That is the beautiful thing. So, this characteristics is in the context of power converter is known as adaptive voltage positioning. For this is particularly used when you are talking about low voltage high current application, when the current can be even tens of hundreds of ampere. Okay. And if there is a 100 ampere load step change, and if there will be a jump due to the ESR, and if it again need to go back, that may take more time, and even if we apply a high gain, the current overshoot can be pretty high. So, this process can cut down the current overshoot, and it will also remove the transient effect, but the penalty, it will shift the DC regulation point a little bit, but if it is within the acceptable limit, then it should be okay. And we can reduce the effective ESR by putting multiple capacitors in the parallel bank in the output. By that way, we can also reduce the droop resistance. So, this will behave like a nearly resistive output impedance, and we will see in that when you do impedance analysis under current mode control. And this technique is also used in microgrid, only the name is different. There we call it as a droop control, and we intentionally reduce the voltage based on the current requirement from, let us say, if it is a solar or any other supply. So, we do this droop control. Okay. Then we can also do energy optimization by means of this. So, with this we have discussed combined feedback and feed forward control, and that offer excellent performance. For voltage mode control, if we apply a supply voltage feed forward, we can get very good audio susceptibility. In load for current mode control, if we apply a load current feed forward, we can significantly improve the transient response, and if we apply a droop control, we can almost cut down, and the output impedance will see like a resistive one. But sensing load current is a difficult task. In case of droop control in microgrid application, the transient performance requirement is not significant. So, in that case, the average current can be obtained, because in buck converter average inductor current is same as the load current, that can be obtained from the average value of the inductor. That means you do not need to sense the load current, and you can do the droop control. But in low voltage high current, where the transient performance requirement is very fast, there the inductor current itself will take some time to slew up. So, you will not get the load feed forward from the inductor average value. So, you may need to either sense load current. In buck converter, we can use a derivative action, or in digital control we can do lot of you can do estimation, and we can very effectively or very accurately estimate the load information. In fact, the present processor, actually the power supply in digitally controlled converter, there is something called power management bus, PM bus, where there is a data as well as the clock communication. So if you communicate with the processor and if you understand the task requirement, in fact you can estimate the load current. By that information can be used to implement such algorithm. So more design aspect will be discussed later, and with this I want to finish it here. Thank you very much.